Hello, I'm Professor Fabrício Cachito from Universidade Federal de Minas Gerais in Brazil, and this is a video pitch for the project Deoxygenation of the Oceans, Past, Present and Future, supported by the Worldwide Universities Network through its Research Development Fund in 2022. This project is an international collaboration between researchers from South America, North America, Africa and Europe, involving collection of rock samples and geochemical analysis in various locations and facilities around the world. Apart from UFMG, we have the participation of researchers from UNESP and UFSB in Brazil, from the University of Leeds in the UK, from the Universities of Ghana and Cape Town in Africa, the University of Southern Denmark, the University of Alberta in Canada, and Stanford University in the US. Oxygen minimum zones are the regions of the world's oceans where oxygen saturation is at its lowest. These zones are currently expanding due to two main factors: warming oceans due to climate change and enhanced nutrient input due to anthropogenic pollution. Regarding climate change, oxygen solubility is correlated to temperature. Colder waters are richer in oxygen, and thus warming oceans causes oxygen solubility to decrease. And in respect to enhanced nutrient input, it applies oxygen concentrations through eutrophication. In areas where human pollution is discharged in the oceans, nutrient-rich plumes develop toxic algal blooms that take over the ocean's surface waters, blocking sunlight and not allowing oxygen to mix through to deeper waters. Expanding OMZs pose a hazard to marine biodiversity and ecological sustainability. Moreover, low oxygen levels in deep waters force shoals or large fish upwards in the water column, where they are more vulnerable to overfishing and increasing temperatures, essentially restricting the marine ecosystem and affecting coastal human communities that depend on fishing for survival. Understanding the history of the world's oceans can provide significant clues to predict and remediate the future. Ancient marine basins, now preserved as sedimentary rocks readily accessible for sampling throughout the world, are the perfect sites for studying the impacts of stressors, such as the rise of atmospheric CO2 on ancient ecosystems. For example, the organization of continental fragments in ancient supercontinents such as Rodinia and Gondwana was very distinct from today's, leading to detectable changes in the distribution of oxygen minimum zones and nutrient availability, and how this affected ancient ecosystems. In this project, we applied cutting-edge biogeochemical tools to study redox, i.e. oxygenation, and nutrient variations in both modern and ancient sedimentary settings, and their impact on ecological complexity and biodiversity. The oceans that formed around 500 million years ago around the continent of Gondwana are particularly interesting for our study, as they contain the remnants of the first complex life forms, such as animals. Those life forms display complex ecological patterns such as predation and high mobility on the seafloor. We collected circa 700 samples from 10 different modern and ancient basins and analyzed them for various biogeochemical proxies such as trace metals, iron speciation, carbon, oxygen, chromium, and cadmium isotopes. Those proxies reflect the degree of oxygenation and nutrient availability during the time of deposition. We then compared the variation in those proxies with fossil distribution in the same samples. Our results indicate the periods of anoxia, i.e. deoxygenation, coincide with the demise or even extinction of various life forms, leading to cascade effects damaging ancient ecosystems. Those periods of anoxia are driven by various factors in the past, such as enhanced weather of continental areas due to climate change and eutrophication. The information gathered from ancient and modern oceanic basins indicate that deoxygenation was the main factor leading to drastic changes in ecosystems of the past. Deoxygenation was led by various natural factors and developed a cascade of effects leading to damaging marine ecosystems and even to extinctions. Today, anthropogenic factors such as pollution leading to eutrophication and climate change are leading to similar loss of oxygen from oceanic surface areas. We are warned by the ancient geological record of the possible dramatic effects of such deoxygenation periods over Earth's ecosystems. We must listen to the cautionary tale of the geological record and act accordingly to prevent similar fate to present-day ecosystems. Thanks for watching, and any questions can be forwarded to my email.